Gravity and the Coulomb force are two of the most consistent laws in physics. Both operate on an inverse square dependence on distance, and both are conservative forces. When these two positive charges are released, they push apart. The repulsion instantly converts stored potential energy into kinetic motion. Every electrostatic field holds energy that remains latent until a charge is permitted to move. To understand electromagnetism, we need to map this invisible landscape. But to be useful, that map must describe the space itself, independent of the specific particles moving through it. To reach that level of abstraction, we have to start with the laws of classical mechanics. We must look past the interaction of individual particles and focus on the mechanical concept of work. We begin with a single stationary positive source charge Q, anchored at the origin. Next, we introduce a variable, a smaller positive test charge Q at a distant point R. The source charge Q radiates an electric vector field E, exerting a force on our test charge Q at point R. To measure the energy stored at different positions, we must move Q from point R to a closer point, P. We must do this with zero acceleration. If the charge accelerates, part of the energy we are measuring is lost to kinetic motion rather than being stored as potential. The electric force, Fe, naturally pushes the test charge away from the source. To counter this, we apply an external force, Fx, pushing Q toward the origin. For our measurements to be precise, the external force must exactly equal the negative of the electric force. The two vectors are identical in length but opposite in direction. By maintaining this equilibrium, the charge travels at a constant, infinitesimally slow speed. With zero net force and no acceleration, the work done by our external force is captured entirely as a change in potential energy, delta U. This raises a question regarding the journey. Does the specific route taken from R to P change the amount of stored energy? This graph tracks accumulated work as the test charge follows three distinct, erratic paths from R to P. Despite the different routes, the final work for each journey is the same. The delta U remains identical. This happens because work is only performed when moving radially toward or away from the source Q. Movements that follow the curve of the field require no work at all. This is the defining characteristic of a conservative force. The total work depends strictly on the initial and final coordinates. The energy equation is concerned only with the start and end points, not the path taken between them. If work were path-dependent, the concept of a stable potential energy field would be impossible. Because the energy depends only on coordinates, we can look at the energy landscape of the entire space. The value of potential energy at a single isolated point is physically meaningless. In practice, physics is governed by the difference in potential energy between two locations. This 3D topological hill represents the energy well surrounding Q. Points R and P sit at different elevations on the slope. Because only the difference matters, we have the liberty to shift the zero point of the system by an arbitrary constant, alpha. Even if we shift the entire hill up or down, the vertical distance between R and P stays the same. The physics of the system remains unchanged. To standardize this, we set the zero point at a distance where the electric field strength effectively disappears. By setting our baseline at an infinite distance from the source, we establish a firm starting point of zero. We define the potential energy of any point P as the work required to bring a charge from that infinite baseline to that specific coordinate. Our map is now structured, but it is still tied to the specific charge we use to measure it. The work we calculate depends on the magnitude of our test charge, Q. As we change the test charge's size, the energy hill's height scales accordingly. To map the field itself, we must remove the test charge. By dividing total work by charge Q, the hill locks into a single permanent shape. The result is electrostatic potential, V, defined as the work done per unit charge. We calculate this with precision by taking the ratio of an infinitesimal amount of work to an infinitesimal amount of charge. By completely factoring out the particle, we have defined an intrinsic property of the space surrounding the charge. We have now constructed a complete mathematical model of the electrostatic potential field. Electrostatic potential is the work required to bring a unit positive charge from infinity to a specific point without acceleration. In this 3D map, a single unit charge moves from the flat edge of infinity up the slope. The counter tracks the voltage accumulated along the path. This model works because we identified the force as conservative, meaning our measurements are independent of the path taken. We standardized the landscape using gauge freedom and isolated the field by evaluating the ratio of work to charge. By analyzing the physical mechanics of a push against a force, we have uncovered the geometric structure of electromagnetism.